So we can, so this is the expression, and this, so this we have the dw here, right? So this is a work done. So what is work done? Work done is normally expressed from your plus 2 class. You know that work done is the is otherwise change in energy in a unit time, right? So work done can be expressed in terms of change in energy. If you take a particular microstate, I can express the change in energy for a particular microstate as minus nRs into dEs. What is nRs? nRs is the number of particles having energy Es and number of particles nr. So if I take one single, if I take for a particular microstate, the change in energy is equal to minus of nRs into dEs. So if I take the average change in energy, so the average change of energy for a microstate it can be expressed as one by script n, where script n is the number of elements into sum over rs, right? I am summing over all the microstates possible into summing over all the microstates possible with the energy of change in energy of one single microstate, right? Which I can always express this as, I can continue putting the negative over here. There's no harm in doing that. Basically, just telling me that there's a work done, right? So minus DES, right? Expectation DES. So therefore, dW is equal to minus DES. Right? So you understood why we are putting the negative there, right? Because the work done is actually reducing the energy, or it is spending the energy. Therefore, we put the negative over here. So DES is the change in energy for a energy level ES. Right. So that is why nRs into DES, and therefore dW is equal to minus DES. So we will substitute this expression over to here, right? So therefore beta dq is equal to beta dE plus alpha dn bar minus beta DES, right? So we substituted this dW into equation 9. So then what will you get? So we are now in a particular situation where if you take the RHS of equation 8 and say this is my equation 11. RHS of equation 8 and equation 11 are same, right? So which means that I can equate the left hand sides of those equation 8 and equation 11, and therefore I can write d of q plus alpha n bar plus beta e bar is equal to beta dq, right? dq is equal to t ds. So therefore beta is 1 by kt, so I can write t ds by kt is equal to ds by k. So d of this one is equal to ds by k. Therefore I can write q plus alpha n bar plus beta e bar is equal to s by k, or q is equal to s by k minus alpha n bar minus beta e bar. What is alpha? Alpha is equal to mu by kt. S by k. So s by k minus mu by kt into n bar minus 1 by kt e bar. S by k, s by k minus so I can express the denominator in terms of kt, and I can write it as ts plus mu n bar minus e bar, right? Now if I expand the value of mu n bar, I can express it in terms of E, Ts and PV. Therefore is equal to Ts plus E bar minus Ts plus PV, right? Minus E bar divided by Kt. So this will come out to be PV by Kt. So therefore, now we know that the Q is equal to PV by KT. So the Q potential of a Grand Canonical Ensemble, which is a very critical term for explaining the statistical parameters of the compound. Why? Because it is having the terms right. So ln of summation of over rs exponential minus alpha nr minus beta es is equal to PV by KT. So therefore this equation basically forms a link between the thermodynamics of the system and statistics of a Grand Canonical Ensemble. So that is the significance of this system, of this derivation and the Q potential. So if you need to calculate the Q potential, one way is to write down its PV by KT, right? And also this equation forms a link between the statistical mechanics and the thermodynamics of a Grand Canonical Ensemble. Okay, thank you.